好，所以我们刚才看到那个反射系数还有透射系数可以用材料的那个本质阻抗还有入射角度、透射角度来表示，而透射角西塔 t 事实上也可以改成那个西塔 i 来表示So the reflection and transmission coefficient at the interface of two media can be shortly described with the material property, that is the intrinsic impedance eta1 and eta2, and the incident angle theta I, which is three parameters specified. You can find the reflection and transmission coefficient. So in this slide, you have the alternative representation by substituting the theta t with theta I using the Snail's law of refraction. But the equation looks a little bit more complicated. And here's the reality check. If you set the incident angle to 0 degrees, that is coming from the normal direction, the representation for transmission and reflection coefficient becomes rather simplified. It comprises only the material property eta1 and eta2, and the formation is consistent with what you learn from transmission line theory. And here is something I mentioned earlier as the translated reflection coefficient. So gamma B stands for the transmission reflection coefficient right at the boundary, but with the help of some phase adjustment. Well, the things I put on the blackboard is a little bit incorrect. Incorrect. So it's not another minus sign, it's a positive sign here, over here. So you should look up at the slides. So here, the effective reflection coefficient can be derived for positioned away from the boundary. Supposing that you are interested at somewhere in front of the interface, say Z, then the effective reflection coefficient can be found as the product of the reflection coefficient and the boundary with phase adjustment. So here the phase adjustment term is beta 1z cosine theta I, that is its projection along the z direction. And because this is reflection, so you go forward and backward. It goes forward and backward. So you need to be counted twice. So you have the 2 factor over here. So the exponential j2 times beta 1z cosine theta I is your phase adjustment with the known property of material beta 1, the known property of the incident angle theta I. You can find the translated reflection coefficient in front of the boundary. Sometimes this expression can be convenient when solving propagating problem. Next, we will look into parallel polarization. So let's check up with the parallel polarization. To the left is the figure for illustration for parallel polarized incidents toward the interface. And for your convenience, I also put the illustration for perpendicular polarization. So what is the difference? What are the differences? The main difference is E-field orientation. For perpendicularly polarized wave, the E-field is pointing outward in the y direction of this interface. On the other hand, for parallelly polarized incidence, is pointing the E field lies on the plane of incidence. Okay, plane of incidence is expanded by incidence, reflection, and transmission. Okay, so for this particular case, the plane of incidence is the xz plane. So the E field lies only on the xz plane. So it has x component, it has projection on the x-axis, it also has z component, it also has projection on the z direction. On the other hand, the H field lies solely on the y direction. So in fact, the H component of parallelly polarized incident is perpendicular to the plane of incidence. So H has y component only, while E has x and z component. And again, here is the incidence, here is the reflection, here is the transmission. You should use your right hand to check up the vector relationship. Check up the vector relationship. So here, oh shoot. All right, so yeah, I need to install the mesh type application into this computer so that the parallel sign can be displayed correctly. All right. Well. 你自己脑补啦哈，自己脑补那个方格子就是那个 parallel sign ，OK。然后在那个 Moodle 上面提供的那个讲义应该没有错了哈。不过这边因为电脑缺那个程式，所以那个 parallel sign 没有正确的显示啊。Alright, so here is the E field representation of the incident wave of parallel polarization. So again, it's the product of the E sub 0 I, the incidence magnitude, and the phase function exponential minus j beta I dot r. The phase constant vector, the dot product of phase constant vector and the position vector, right? And the things that you need to be aware is the representation for the incident field. E sub 0 I should be written like this. It has projection on the x and z directions. So it's written as cosine theta I, x cosine theta I minus z sine theta I. So because the E field over here has its projection on the x-axis is positive, while its projection on the z-axis is negative, so that it can comply with the right-hand square rule. And as expected, because this is TEM wave, so the E field, the dot product of E field and the incident phase constant vector is 0. Should be 0 because of TEM wave condition. And here is the representation for the magnetic field. And we use the same relationship to derive the magnetic field representation using the phase constant vector and E field description divided by eta 1. And you can find that it lies solely on the y-axis. Okay, so you need to derive that. You need to derive that relationship at home. Okay, now to check, it's the cross product of beta I and EI end up with y component only. 事实上，它会变成是一个，那事实上会变成是一个什么？sin 平方西塔 i 加上 cos 西塔平方 i 所以等于1，然后它的方向都在 y 方向。 Right. So here is the reflected wave. Okay. So again, we write up the reflected wave description, and this is wrong. Damn, this is wrong. I missed something. 有没有看到哪边漏掉了 ？Reflection coefficient. Okay. Reflection coefficient gamma parallel should be put over here. Okay, so this, that's correct. Okay, that's correct. Is that correct? Yeah, it's correct. Yeah, it's correct. I should check out with this. 好了，他写这边是 parallel 啦，他写10R 是 OK 的啦，10R OK 也不算错了哦。然后这是贝塔 R 是你的那个反射的 phase constant vector. That's the phase constant vector for the reflection. And this one should be corrected with E sub 0 I. Okay? E sub 0 I. And the gamma should be corrected as gamma parallel B. Suppose that means that indicates that this belongs to the reflection coefficient at the boundary. Okay. And here's the direction of vibration. As I can see here, for the reflection part, the projection become positive on both x-axis and z-axis. While for the incident part, the projection on the z-axis is negative. But for a reflected wave, it's pointing this way, so the x and z axis projection are both positive. And again, the reflected E field is perpendicular to the is transverse to the propagation direction. So the dot product of ER and beta R are is zero. And the bottom is the magnetic field intensity representation. Again, it can be found by beta R cross EI, and you can see it lies on the y-axis only, but it's pointing toward the negative y direction. So as you can see, the two red dashed line circles, the HI is pointing to positive y direction, while the HR is pointing toward the negative y direction, so that the right-hand screw relationship can be complied. 所以自己要动手操作看看啊。最后我们来看透射波。So let's check up the transmitted wave representation. So the original representation for transmitted wave like this. You have the magnitude part and the phase function part. And here is the description for transmission phase constant vector. And as you can see, it comprise the material property beta 2 and direction description. That is sine theta t on the x-axis and cosine theta t on the z-axis. So it's simply the direction of the red arrow, Then the E field, the magnitude of transmitted field, can be rewritten as direction description and the product of the incident. So here I would like to put I superscript over here. So the incident field, magnitude, and the transmission coefficient. So that would be the red circle is the parallel transmission coefficient. Okay. And again, the vibrating direction of the E field and the propagating direction of the wave is transverse. So the dot product is 0, And to the very last is the representation for the magnetic field. Again, it's pointing on the y direction, and it's positive as well as the incidence. So the very last equation over here is only different toward the incident wave by the addition of transmission coefficient of parallel polarization. All right, now we can combine the three representation, the incident wave, transmitted wave, and reflected wave, using the boundary condition. Again, we have no surface current on the interface, so we have continuous tangential H field as well as continuous tangential E field. So we look at the total E field and total H field. No, not total E field. Sorry, I'm wrong. We look into the difference of E field and H field at the interface. So we look at Z equal to 0. Or we look at Z equal to 0. We look on the two sides. On the median two side, you have transmitted wave only. On the median one side, you have incident wave and reflected wave. You use Z cross this to get the tangential component. And for S component, the tangential component is in which direction? Is in the X direction. On the other hand, for magnetic field, the tangential component is on the Y direction only. So you end up with ES component and HY component. All right. So you have equation 1 and equation 2. So the ES component look like this. A little bit messy, I admit. And here's the H component on the Y direction, right? Then you apply the Snail's law of reflection and the Snail's law of refraction to simplify equation 1 and equation 2. And after a couple of minutes, I suppose, you can end up with equation 3 and equation 4. Equation 3 is look like this. It's a little bit different from what you have for perpendicularly polarized wave, but for now you probably won't be able to tell the difference. Okay, but that's fine. That's fine. And so here's relation 3 and relationship 4, and you massage the two equations a little bit. You will end up with the reflection coefficient and transmission coefficient at the boundary for parallelly polarized wave. The formats look familiar with the perpendicularly polarized part. Right? For the reflection coefficient, you have some summation in the denominator, in the denominator, and some subtraction in the denominator, and you have, they are in similar format as what you have for the transmission coefficient. But if and of course the theta t angle can be substituted with theta I angle and beta 1 and beta 2 relationship. For reality check, if you set the incident angle to 0 now, that is the normal incidence, you end up with familiar relationship like for reflection coefficient, it's just eta 2 minus eta 1 over eta 2 plus eta 1, and the transmission coefficient is familiar as well, that's 2 times eta 2 over eta 1 plus eta 2 跟之前是一样的跟之前一样的 normal incidence 的时候垂直parallel polarization. For normal incidence, the parallel polarization and normal and perpendicular polarization should yield the same reflection coefficient and transmission coefficient. But if you compare the reflection and transmission coefficient at the boundary for perpendicular polarization and parallel polarization with an oblique incident angle, that you have a non-zero theta I. If you check up the two, can you tell the difference? For perpendicular polarization, cosine theta I go with eta 2. For parallel polarization, cosine theta I goes with eta 1. So they are actually different because of the boundary condition, the difference in the boundary condition. Because of the difference in tangential component, So you found, if you compare the two carefully, you found the location of eta 1 and eta 2 are interchanged with perpendicular polarization. So for perpendicular polarization, you start with eta 2 cosine theta I minus and plus eta 1 cosine theta t. For perpendicular polarization, you have eta 1 times cosine theta I minus and plus eta 2 times cosine theta t. So the main difference between the two is the eta 1 and eta 2 position are interchanged for perpendicular and parallel polarization. 好，那这个交换的结果其实很严重，也就是说，当你的入射波的角度偏离正向入射的时候，它们的反射系数跟透射系数的差异会越来越大。只要你是接近正向入射的时候，两者会有一点点差异。只要你是刚好正向入射，那就是没有差异。因为你刚好正向入射的时候，你的 cosine theta I 跟 cosine theta t 都等于1。For normal incidence, theta I and theta t equals to 0 degree. So cosine theta I and cosine theta t equals to 0. To 0 for the two cases. I'm sorry. 我刚刚忘了一点记住我这边还有一个 minus sign 我刚刚在 check 那个正向入射的时候才有看到所以除了 eta 1跟 eta 2的位置交换以外，这边还有一个 minus sign Now that there's a minus sign for the reflection coefficient representation for parallel polarization. Okay, so for theta I equal to 0 degree, you have eta 2 minus eta 1 over eta 2 plus eta 1. For here, if theta I equals to 0 degree, you have the minus of eta 1 minus eta 2 over eta 1 plus eta 2. So they are the same for normal incidence. So is the transmission coefficient case. But as your incident direction is steer away from the normal incident direction, the two becomes different. And then end up with several interesting results. The first interesting result we'd like to check up is the Brewster angle phenomenon. And we will also check up with critical angle phenomenon. Okay, they are the causes for many interesting propagation phenomena, and they are used for some specific application. So Brewster angle means total transmission, zero reflection. Brewster angle is defined as an angle with no reflection and total transmission. Critical angle is defined as an angle with no transmission and total reflection. But in fact, the two phenomena are not suitable to compare side by side because Brewster angle only happens at one specific angle. Brewster angle only, total transmission only happens for one specific angle, while critical angle is something that you get total reflection if your incident angle is greater than critical angle. If the incident angle is greater than critical angle, you got total reflection for any incident angle beyond the critical angle 啊。所以这边要讲的是 boosted angle， 它只有在特定频率才会发生 total transmission， 而全反射角 critical angle direction 它比较像是一个 threshold， 比较像是一个边界。你只要入射角超过 critical angle， 那么所有的结果都是 total reflection， 都是 total reflection。但是你看到 critical angle 后面的那个说明的后半段的时候，你会发现，即便都是 total reflection， 它们的结果还是有些不一样。只要你的入射角超过那个 critical angle， 都是 total reflection， 但是它所产生的结果还是有点不太一样啊。你有不一样的入射角的时候，所对应到的结果还是不太一样，所以这会那是会是比较细微的差异啦哈。我们到后面的时候会讲到 ，OK。So we will examine perpendicular and parallel polarized wave to see if it is possible to find solution for boosted angle. What are the conditions necessary to have boosted angle and critical angle? So let's check up with our first question is. For perpendicular polarization, total transmission happens at a boosted angle. Can we find that? Can we find the boosted angle for perpendicular polarized wave? Okay, so suppose the boosted angle is available for perpendicular polarized wave, then and we refer it as theta b. Now, B stands for boosted angle. So if we do have total transmission at a boosted angle for perpendicularly polarized wave, then the reflection coefficient should be 0, right? And the relationship between this is what relationship? This is the Snail's law of refraction. This is the Snail's law of refraction. So cosine theta t is replaced with with theta b. Okay, and you proceed with this relationship further. You end up with the criteria is derived from this relationship. If you want to have 0 reflection coefficient, then the denominator should be 0. So you end up with this relationship. And if you massage this equation a little bit, you have the sine of theta b. And you end up with this result. So let's check up if can we meet this condition for true medium. So you see the sine of the boosted angle can be fully described using material property of eta 2 mu 2 and eta 1 and the eta 1 mu 1. And the most critical part is the denominator over here. Mu 1 over mu 2 minus mu 2 over mu 1. Then we realize you're supposed to realize one problem. For non-magnetic material, mu 1 equals to what? Mu sub 0. Mu 2 equals to what? Mu sub 0 2. 对于非磁性材料，我们的介磁系数大概都离 mu 0相距不远。一般的非磁性材料，你的那个介磁系数几乎都等于 mu 0。So for non-magnetic material, mu 1 and mu 2 are nearly the same. So therefore, you end up with 1 minus 1 in your denominator. So can you have true? So the thing goes up to infinity. Okay. So do you have a real solution for theta b in this case? Well, no. Okay. So but You may have a real solution for theta b if you have magnetic material and non-magnetic material. So if mu1 and mu2 are of different value, then you might have real solution for theta b. But for most material, for most non-magnetic material, this turn approaches to, sorry, I'm sorry, 这边写错了啊. This turn approaches to 0. This turn approaches to 0. So the sin theta b goes to infinity. Therefore, you don't have real solution for theta b if you have non-magnetic material on both sides. So the general case, for the perpendicularly polarized wave, you don't have real solution for Brewster angle. Because the sign of a Brewster angle must lies between 0 and 1. Okay? So if mu1 equals to mu2, sin theta b equals to infinity, so you don't have real solution angle. Okay, so the conclusion is no Brewster angle for perpendicular polarized wave. No Brewster angle for perpendicularly polarized wave. Okay? So how about parallel polarized wave? So how about for parallel polarization? Brewster angle happens. Brewster angle can be found. Okay? Using the similar procedure. Use the similar procedure. You end up with the psi of theta b, which can be represented with, again, with epsilon 1 mu1, epsilon 2 mu2. The good thing is the denominator part is epsilon 2 over epsilon 1 minus epsilon 1 over epsilon 2. This thing is non-zero as long as epsilon 1 is different from epsilon 2, which can be easily satisfied for most material. For most material. For most interfaces with non-conducting dielectrics, the solution is real. The real solution exists. So for parallel polarization, the Brewster angle can be found using this relationship. So suppose you still have non-magnetic material, so mu1 over mu2 is 1. Is 1. Then mu1 over mu2 is 1, then you can massage the equation a little bit. You found that the sin theta b is the square root of epsilon 2 over epsilon 1 plus epsilon 2. So here is your Brewster angle. That is the arcsine of this. And you can also find the Brewster angle using this relationship. But okay, so here is the so you have sin theta b. So here is this is the sin theta b representation, and this is the cosine theta b representation. So if you divide the two, you end up with tangent of theta b. Tangent theta b. And tangent theta b becomes the square root of epsilon 2 over epsilon 1. Okay? 因为这样讲啦，第一式跟第二式都可以给你 Brewster angle。只是你把第一式除上第二式之后，它给你一个比较容易记的 Brewster angle 的表示式。好不好？所以这三式其实都可以啊，反正你有 epsilon 1跟 epsilon 2，你就可以找得出 Brewster angle。只是说这几个式子里头最方便记忆的可能是红框框里头。So in the red box, you have the most simplest relationship between material property that are epsilon 2 and epsilon 1 with respect to your Brewster angle. So boosted angle can be found simply by taking the arctangent of square root of epsilon 2 over epsilon 1. Okay, so as long as epsilon 1 is not the same as epsilon 2, you will have a boosted angle for parallel polarization. So in general, only parallelly polarized wave can have a booster angle, can have a booster angle. 只有平行极化会有 booster angle 的解。好了，那它有什么用途？ What are the application for booster angle? Well, actually, it's do applied. The booster angle relationship do applied in one particular application. It's used. This application is TV signal, TV broadcasting signal. Okay, you know that electromagnetic wave was found by Maxwell about 140 years ago, predicting with Maxwell equation. Unfortunately, Maxwell didn't witness the validation of electromagnetic waves. He predicted, but he didn't observe it. After the death of Maxwell, which is around the age of 42 or 44 something, okay? After a few years, Hertz invent an experiment to demonstrate the electromagnetic waves. Okay, so the first time the electromagnetic wave is generated by, electromagnetic wave in radio frequency is first demonstrated by Hertz about 130 years ago something. Okay, and in the early age of EM wave development, we don't have bidirectional wireless communication because the transmitter is complicated and expensive. Receiver, on the other hand, receiver are more cheap. They are cheaper and simpler. So in the early age of wireless communication, the communication is more or less one directional, unidirectional. So it's like broadcasting, the radio and TV broadcasting. TV broadcasting was commercialized about 70 years ago, after the World War II. Okay. So by that time, scientists have more knowledge about electromagnetic waves as well as the propagation environment. So when it comes to the determination of TV signal polarization, they decide to have horizontal polarization. Okay, that's kind of strange because at an early age of wireless communication, we often opt to use vertical polarization for point-to-point communication on the land, on the Earth. Why? Because vertical polarization can be provided with a simple dipole or a simple monopole. Erect a piece of wire, then you have vertical polarization. So at the other end, at the receiving end, as long as the person have also a vertical piece of wire, you can receive vertically polarized wave. So it's simple. It's quite straightforward. But for TV signal, we opt to have horizontal polarization. And when I was a kid, most of the building in Taipei are 5-floor apartment. Okay, and if you get to the top of the 5个公寓啦，5楼公寓的那个楼顶 ，you will find that every household have their own TV reception antenna. That is the Yagi-Uda antenna. I believe you guys already should already know that, and they are all pointing toward the north of Taipei, which is the location of Zhuzisan, because you have the TV broadcasting tower is that place. And all the Yagi-Uda antenna are aligned horizontally, because the TV signal are generated in terms of horizontal polarization. So my question to you is, for TV signal or for signal on the Earth, the vertically polarized signal is perpendicularly polarized or parallelly polarized? Well, depends on the interface you are talking about. The interface that we are talking about is the so-called iron sphere, which is located about 10 to 20 kilometers above the atmosphere. And the cause for the iron sphere is because the solar wind, 太阳风, the highly energized particle in the solar wind will break down the gas molecule in the atmosphere. So you have positively charged iron and negatively charged iron. So on the top of the atmosphere, you have a layer of gas that contains positive and negative ions. And because you have positive and negative ion, the iron sphere is slightly conducting. It's slightly conducting. So its material property are different to the atmosphere near the Earth, near the Earth's surface. So you can think of that as an interface. Okay, so based on our knowledge of atmosphere and ionosphere, so engineers decide to use horizontal polarization, because horizontally polarization on the Earth is the so-called perpendicular polarization in terms of the ionosphere and the atmosphere's interface. 相对于电离层跟大气层跟电离层的界面，水平极化的场型，相对于那个界面，你自己观察一下嘛，你的那个 incident plane incident plane 是这个方向的，那你的水平极化是这个方向，所以它是不是所谓的 perpendicular polarization？ 所以既然是 perpendicular polarization 的话，它就找不到 booster angle。意识就不会全透射，它不会某个角度出去就出去了。那意识没有全透射，意思是有些会反弹回来。那反弹回来，意思它就可以传到比较远的地方。那70年前那个发射机还很贵，所以你用 horizontal polarization 的话，你的那个电视塔可以 cover 比较大的范围。所以为了省钱，所以我们选水平极化，为了省钱So the reason why we choose horizontal polarization 70 years ago is because the wave can be regarded as perpendicular polarization from the perspective of atmosphere and ionosphere interface. And because perpendicular polarization has no booster angle, has no total transmission, so more or less the incident wave will be reflected more or less, so that if you choose horizontal polarization, you can cover a larger area for those TV broadcasting tower. Okay, so that decision was made based on economic consideration 在 economical consideration 从经济上面的考量，我们决定采用 horizontal polarization。所以相对的，假如你用 vertical polarization 的话，你是有机会形成全透射的total transmission 的。And here is another interesting fact about booster angle. And well, so let's look at it. Ground reflected right-hand circularly polarized signals is transformed from right-hand circular polarization to linear polarization, then left-hand polarization as the incident angle increases. So the incident angle defined here is the theta. The incident angle defined here is this theta angle. Okay, this theta angle. So that should be put into different signs. Okay, and in terms of GPS signal, we know that GPS signal is right-hand circularly polarized. So if you want to receive the GPS signal, you should have a right-hand circularly polarized antenna facing upward. However, if the signal goes to the ground and getting reflected, then the reflection become kind of strange. Okay, so if the incident angle is, so this is the theta value. If we look at the angle for theta between 90 and 180 degree, that is going from, you found that the reflection is right-hand circularly polarized if you have a smaller theta angle, but it becomes linearly polarized for 115 degree incidence. Because this is the booster angle between air and the Earth, supposing the dielectric constant for Earth is 4.5, then you can have a booster angle. You can have a booster angle for parallel polarization. And because you don't have a booster angle for perpendicular polarization, so at the angle of 115 degree, you have reflection from perpendicular polarization, but you have no reflection from parallel polarization. So the reflection is transformed from right-hand circular polarization into linear polarization. Okay? And beyond the booster angle, the parallelly polarized wave, the reflection coefficient of the parallel polarized wave change its sign. So it becomes left-hand polarized. Because I should not put circular polarization. Circular polarization only happens at this point at 90 degree and 180 degree. But anything between is right-hand polarization, and anything between 115 and 180 is left-hand polarization. Let me put it this way. This is the reflection coefficient at the interface. If you use epsilon equals to 1 and 4.5. So the red line is the reflection coefficient for perpendicular polarization. So it goes from -1. If we are looking from the very from the zenith direction 从上面直接看的话，你从正向入射，你从上面直接看的话 ，perpendicular 跟 parallel 的反射系数都是-1，都是-1，因为从1到4.5，所以正向入射的时候都是-1。可是当你的角度开始倾斜，不是正向入射的时候，这两者就产生区别。但对于正交极化，也就 perpendicular polarization 来讲，它从-1，然后一路到大概-0.4、0.5、0.4左右，就它已经切得很平的时候，从水平那个方向切过来的时候，它的反射系数还是负的。 可是对于 Parallel Polarization 来讲，它一开始是-1，到了115度的斜向的时候，它变成是0 booster angle， 再过来它变成是正值啊。所以，假如你原来是右手圆极化，在这里还是右手圆极化没问题，在这个区域也算是右手极化啊。但是到这个地方，你会发现两个大小相同，但一个是正的，一个是负的，所以你的反射就从右手极化变成左手极化，所以甚至是左手圆极化，然后在这边的话呢，都是一正一负，所以是左手极化。这边是一个负值配上一个0，所以是线性极化。Okay, so here again we are propagating from epsilon r equals to 1 to the Earth's material, so that epsilon is 4.5, and because of the reflection coefficient behaves differently for perpendicular and parallel polarization. For perpendicular polarization, the reflection coefficient is negative for all incident angle, from -1 to -0.4, 0.4 something. On the other hand, for parallel polarization, the reflection coefficient change more dramatically. This starting from -1 to 0 for the booster angle, all the way up to 0.4 for grating incidence. 从侧面进来 grating incidence. So if you're taking the combination of the two, you have right-hand circular polarization for normal incidence, left-hand circular polarization for grating incidence. 从180度侧边过来 and linear polarization, because you have no reflection for the parallel component. Therefore you have the linear polarization wave for booster angle. So that's one interesting result when it comes to reflection of oblique incidence. And the next thing we'd like to discuss is critical angle. So on the contrary to booster angle, critical angle happens. The requirement for critical angle is total reflection, no transmission. In other words, no transmission. But the term no transmission should be examined carefully once we have learned as we proceed further. Okay. So let's take a look at the perpendicular polarization, and to make your life a little bit easier, we assume the medium is lossless. Okay, lossless medium. So here is the this is what? This is the reflection coefficient representation, and it requires to be 1. Okay, so the denominator and numerator. And the condition can be changed into this. That is, we want the imaginary part for, we want theta t to be an, well, okay, let me put it in this way. What is total reflection? Theta t, which total reflection means the transmission angle theta t is greater than 90 degree, or is 90 degree or greater. So cosine theta t needs to be a value greater than 1 or smaller than 0, So if the solution for theta t is an imaginary number, then you don't have a real solution for theta t, then you have no transmission. 所以这边就是说，我们让透射角变成无解也就是你找不到西塔 t 的解的时候，也就是 cosine 西塔 t 的数值介于正负1之外的话，那你就是一个，或者说 cosine 西塔 t 是一个虚数的话，那你就 没有 transmission. So providing that cosine theta t is an imaginary number, then you don't have transmission. So to have an imaginary solution, if you want to have if you want to set cosine theta t into an imaginary number, then this part must be smaller than 0. Okay, so the requirements become that this thing must be greater than 1. This thing must be greater than 1. And when this thing is equals to 1, you have the so-called critical angle. So if the incident angle is greater than the critical angle, if the incident angle is greater than the critical angle theta c, then you have no solution for theta t. So with these requirements in mind, you end up with this relationship. The critical angle theta c equal to arcsine of this. So to put it more simply, supposing that the two materials are non-magnetic material, then you have mu1 equals to mu2 equals to mu sub 0. So this representation becomes simpler as the arc sine of the square root of epsilon 2 over epsilon 1. Then we can find that if epsilon 2 is greater than epsilon 1, then the square root of this is greater than 1. So the arc sine of a number greater than 1 will end up with with no real solution for theta c. 所以从反射系数我们一路推导到我们看到要有全反射角 total reflection 的条件是，当你是高介电系数材料，你的入射波是从高介电系数材料到低介电系数材料的时候，你是有可能遇到全反射角的，Let me finish the derivation first. Okay, so here it is. We suppose mu1 equals to mu2, so the critical angle theta c can be found as this. So theta c is real if epsilon 2 is smaller than epsilon 1. Means that the wave must propagating from a high permittivity material into a low permittivity material. On the other hand, if the propagation is from low permittivity material to high permittivity material, then you have a transmission all the time. So remember to put it more simply, suppose we have Snail's law of refraction. So if you have an incidence like this, what is the direction of the refracted wave? This refracted wave, theta t, will make a smaller angle if you are propagating from low permittivity material to a high permittivity material, right? So on the other hand, if you are propagating from a high permittivity material to a low permittivity material, the theta t direction will steer away from the normal incident direction. So if you increase the incident angle to a certain degree like this, then you end up with a transmission aligned with the interface. align with the interface. Then you have no transmission in the low permittivity region, right? 啊，所以你只要从高介链系数的材料传到低介链系数的材料，当你的角度超过 critical angle 的时候，你根据 Snail 的折射关系，它就没有 real solution。但是注意的是，这是啥？这个东西是什么东西 ？This is the so-called surface wave. That can make that makes an interesting topic in electromagnetics. Actually, some application tries to employ the phenomena, this surface wave phenomena. Okay, so we will discuss that later. But okay, the first thing you notice that is, if you're propagating from high permittivity material to low permittivity material, if the oblique incidence angle is big enough, you have no transmission. No transmission. No transmission suggests you have zero reflection. Well, I think I will leave the discussion for surface wave next week. So I am still a few slides short. So let's continue, all right? Let's continue so we can have break earlier, all right? So at the critical angle, theta c, to have a real solution, epsilon 2 must be smaller than epsilon 1. So you need to propagate from high permittivity material to low permittivity material. And the reflection coefficient, what happens with reflection coefficient for theta I greater than theta c? The result is the reflection coefficient, the magnitude of the reflection coefficient is 1 when your incident angle is greater than critical angle. What is the hidden message of this equation? Why I put the absolute sign on the side of the reflection coefficient? That means if your incident angle is greater than the critical angle, the reflection coefficient, the phase of the reflection coefficient shall change. The magnitude stays as 1 for all incident angle greater than theta c, but the phase of the reflection coefficient change for different incident angle. OK? 所以这是比较好玩的地方啊。当你的入射角超过西塔 c 超过 critical angle 的时候，不是说超过 critical angle 就什么东西都一样了啊。全反射这件事情都一样，然后反射的能量等于1这件事情也都一样啊，但是在界面上发生的事情会有些不一样啊。那个就属于我们在讲 surface wave 的那个部分啊。Alright. So assume beta 2 is smaller than beta 1. That is, beta 1 is a high, medium 1 is a high permittivity material. Beta 2 is a low, medium 2 is a low permittivity material. Therefore, the critical angle theta c is real. You have a real solution for theta c like this. As the arcsine of beta 2 over beta 1. Okay, 希望我收音还收得到。All right, so the transmission angle, the cosine theta d becomes this, and you don't have a real solution for this, so you don't have transmission. But you have an imaginary solution. This becomes an imaginary number. This becomes an imaginary number. And for theta I is smaller than theta c, you do have a real solution for theta t. But as you can see here, the angle theta t is greater than theta I, so it's tilting toward the grating direction. 我不知道你们知道 grating direction 是什么意思？正交 normal direction 你知道吗？所以跟 normal direction 垂直的，也就是到侧边的，叫做 grating direction。那 the direction grating direction comes from, I believe, it comes from the term cheese grater. So if you want to have cheese, usually you buy a big chunk of cheese. So anytime you want to have salad, you use the cheese grater to cut thin slices from the big chunk of cheese. Okay, and the blade of the cheese grater must come with a very low angle on the cheese surface, so you can have thin slice of cheese. Because cheese is expensive, right? I mean, hard, solid, aged cheese is kind of expensive. So you just cut some thin slice of cheese to add on your salad. Okay. So the grater, the blades of the grater is nearly in parallel with the surface. So we refer it as the grating direction. Okay. And so for total reflection, total reflection at the critical angle, cosine theta t goes to 0, which means theta t goes to 90 degrees. So the second half of the transmission coefficient, second half of the reflection coefficient goes to 0, because cosine t is 0. So you see there is a great difference between parallel polarization and perpendicular polarization. At the critical angle, the reflection coefficient for perpendicular polarization is 1, while the reflection coefficient for parallel polarization is -1 at the critical angle. So the two are quite different. So is the transmission coefficient. The transmission coefficient for perpendicular polarization is 2, while the transmission coefficient for parallel polarization is this: 2 times eta 1 over eta 2. 2 times eta 1 over eta 2. So they looks quite differently. And if you look at the phase constant vector of transmission, which should be represented like this. The x component is sine theta t, and the z component is cosine theta t. You have the x component sine theta t becomes 1 because cosine theta t goes to 0. So beta t equals to beta 2 at the x direction only. So you actually has a transmitting wave along with the interface, because its propagating direction aligned with the x-axis. So it's propagating along the surface. So the transmission happens, but it happens on the interface. It has x component only, no z component. So it does not go into median 2. It propagates on the interface between median 1 and median 2 at critical angle. So here is the critical angle phenomenon considered in terms of incident wave, reflected wave, and transmitted wave in terms of Poynting vector. So we know Poynting vector is the product of E field and magnetic field. So here is the incident wave. As you can see, the magnitude equals to E sub 0 to the square divided by 2 and eta 1，就是1/2的 b 平方 r 啦，1/2的 b 平方 r 的意思啦。但是呢，它有
带前面这个向量，告诉你传播方向啊。So the second half of the representation tells you the amount of incident wave power density, while the first part, the small parenthesis, tells you the direction of incident wave. For the reflected wave, again, the first part tells you the direction of reflected wave, and the second part is the magnitude. If you compare the two, you found the magnitude are the same for the incident wave and the reflected wave. So you have the so-called total transmission. However, if you look into the transmitted wave, the Poynting vector of the transmitted wave is non-zero. It's non-zero. You still have something. You have this. Unfortunately, well, I should put it unfortunately. In fact, the beta t, the propagating direction of the transmitted wave, is along the x-axis. So you do have energy flow along the interface, but no energy flows into the median 2. So therefore, at a critical region or beyond the critical region, you have the so-called surface wave. The incident wave will produce surface wave along the interface, but nothing goes into median 2. Okay. So here is the case for incident angle greater than critical angle. So I have warned you earlier that you shouldn't treat all incidents beyond critical angle the same. Even they are beyond the critical angle, even all the energy are reflected, the surface wave are somewhat different for different incident angle. So here we are. If theta I is greater than theta C, is greater than the critical angle, you do have a solution for cosine theta t, which is purely imaginary. Okay, and you can see that cosine theta t, though is purely imaginary, is still a function of theta I. So for different theta I, you end up with different values over here. Even though that you have no real solution for your transmitted wave, and then it will leads to the so-called surface wave. So-called surface wave, that you have a power flow propagating along the median interface. This phenomenon is referred as the surface wave, which plays an important role for wave scattering and advanced antenna design. So the surface wave is also used for antenna design as well. I guess I will stop here and we'll continue to discussion of surface wave and discussion for low C median transmission next week. All right， 好，那我们今天到这边。那个比较晚来的同学，你那个考卷可以过来拿。